Get the record going while people are trickling in.
Dan, that file link that you sent, I couldn't get it opened
I just,
whatsoever.
yeah, I saw your email, and so I just changed the settings, so you should be able to now.
Okay.
So give that a go while we wait for people to trickle in. And usually when I attach a file that's too big, it goes straight to the Google Drive, but I always thought it set the permissions so anyone who's receiving the email can grab it, but I guess not. Too many things to keep up with these days. I can't remember what does what.
Taking a little while to download.
It's big, yeah.
Yeah.
That's okay. We won't need it till the second half of this today. Got more people coming in. Hey, everyone. So we were just saying that file I sent around didn't have the download permissions set correctly. They are now. And so you may want to grab it now because it's a big file. It'll take a while to download. And once you download it, you can start uploading it into Afterglow. We won't need it till the second half today, but it's something you can do in the background. So we don't have a delay later on when we get to it. All right, let me set up my screen here for Sharon. See, we have two more. I can't tell since I repositioned my screen, so I'll just repeat the message again. The big file that I sent around, the download settings weren't set correctly. They are now, so go ahead and download that and upload it into your workspace in Afterglow. We'll use it a little bit later on, but it may take a while to download and upload. So probably do that in the background. Let me move the Zoom controls over, put up the chat. Okay, how is everyone? Summer starting well? Okay,
So
let's
far,
see.
so good.
So far, so good. Yeah.
Still finishing spring.
Oh, well,
Yeah, almost there.
I feel sorry for you then. I'm very happy to be done with spring. Um, though, I taught MWU this past spring and I was really happy with it this year. It was the third time I taught it. The first time is, flying by the seat of my pants, and I was pretty happy given that. The second year, I decided to let a bunch of students in who didn't meet the prereqs, and the prereq was any astro or physics course. And that didn't go as well as I would like. I learned that they do have to have you have to take at least some course in astro or physics first, at least for the number of modules I do. If you're going to do half as many modules and supplement it with more background material, that could be fine. But if you're doing like the grand tour of all of them, they better have some astro or physics background. But this time I enforced the prereq and very happy with it. I got student evaluations back, and they're back where they were in the first year. So feeling pretty good about it. Anyway, today we're going to finish module 6 and begin module 7. So I am sharing and I'm recording. Let me just check. Yeah, I'm recording and I am sharing. So, okay. So last time we started module 6. So we're into module 6 and 7, the final two modules. We skipped 5C, which is kind of gravitational waves, black holes, because it's not done yet, but we'll dabble with that in the weeks to come. We've made some progress there, and so we'll wrap up our run this spring and into early summer with gravitational waves in a week or two. But Module 6 and Module 7, they're galaxies. The course runs from nearby to far away, just like the Opus course does. Though, the Opus course is more about the cosmic distance ladder. This is very orthogonal to it. And so in 6, we start with radio. And then in 7, it's a capstone. Each team picks a galaxy from a diversity of galaxies, covering all of the galactic evolution parameter space, hopefully, if you can convince them. I found all my students want to do pretty spirals. No one wants to do ellipticals and whatnot. So it's always a challenge to cover the full parameter space. But yeah, 7's the capstone. It involves optical and mid-infrared and radio and just all the stuff that they learned. But yeah, 6, we're still building up that radio skill set, and they're learning how to use the Doppler effect in 2 different ways, imaging and spectroscopy. So we did the imaging part last time. We did that on Andromeda. It's hard to find objects big enough that we can resolve in the radio. Our beam is about 3/4 of a degree. So there are only a handful of things, and Andromeda is one of them, being 3 degrees across. And so the students make a map over that region, and we went through the steps of processing it, and both processing it in Skynet to make FITS files, and then how to combine the FITS files into LRGB plus narrowband using the same kinds of techniques they've been learning in the optical. So it's good reinforcing stuff, but they get something totally different. As we're sitting here and we saw last time, you see Andromeda there. You see it is resolved just barely. And you can see its rotation in color because we're making use of the spectral information. So that was cool. And the students really liked this, somewhat to my surprise. I heard more, this is cool, than perhaps in any other module. Okay. And, well, part of that may be, like the optical stuff, like making their star forming region image is really cool. It's just spread out over so many weeks as they're ramping up on that skill set. This is like a 1 week or even 1 class activity. So it's very quick and they get this cool result and they like it. And it's not just the image, it's the calculations. And we did the calculations last time. We're going to do similar calculations this time. We had myself and 3 brave souls do calculations last time. And basically from the center frequency, which corresponds to the green color, the middle of the galaxy, as the bands were set. And then one of the edge frequencies of one of the bands, either the red or the blue, we calculated such cool things as how long until Andromeda collides with us and the enclosed mass. We also had to make a measurement of the size of the galaxy for that. Okay, so now we're going to do similar things, but with galaxies that are farther away. They're still relatively nearby in the universe, but they're far enough away that they are less than 3/4 of a degree. So we could do it as an image, but it's just going to be a blob. So instead, we're going to just do a straight up spectrum. And one of the advantages here is instead of, see, for this image here, I had to kind of give them the filters. Like green will be from here to here, and red and blue. And so the central frequency, the edge frequencies were decided by how I chose to break up the band. So I kind of picked that for them. Here in the spectra, you can measure those things for yourself. That's what we're going to do. And let me go to the module guide here. So this is the module 6 guide. I'll just pop back up to the top. So we start with Andromeda and the processing of it. That's all there. And then down here near the end, you can see we've gotten through most of it. This part's not that hard. We give them 7 potential targets. I tried a whole bunch. And these are all edge-on spirals. And so from the subset of galaxies, there are spirals that are also close to edge-on. These are the ones that work. And I've marked 4 of them as easy and 3 as difficult. And I tell each team to pick 1 of each, 1 easy and 1 difficult. And they collect the data. And it's fairly easy to do. I guess I should demo that. That wasn't part of my plan, but I can sort that out quickly enough. I'll just demo it, then we'll use some acquired data. Radio observing, add a new observation. And let's do this one right here, NGC253. And the optical file that you're downloading and uploading into Afterglow in the background, it's also this galaxy. It's a very nearby spiral galaxy, the Sculptor galaxy, edge on spiral. And so it satisfies the radio criteria too, plugs in the coordinates here, and all this is good. We don't really have to worry about observing only at night. The sun can mess up images, but it's not really going to mess up a spectrum. Any interference from the sun bouncing off the struts will cover the whole spectrum. And so it's not going to be a problem. So I picked my target. We're in high frequency mode. And for these, I do kind of shift the band a little bit. And this is described in the guide. You automatically get two of these high resolution spectra, just like with Andromeda. I just shifted down a little bit because Andromeda is blue shifted towards us. All these galaxies being farther out in the universe, they're cosmologically red shifted. So I just shift everything a little bit, keep all the action in that second higher frequency band. And the two numbers have to be separated by 15.625. And so basically I set this at 1419, then subtracted that off. If you forget to make the change, it's not a big deal. It'll be somewhere in the two spectra. And then instead of doing a map, like we did with Andromeda, I'm going to do an on-off observation. And these are pretty simple. For these, we're going to do 300 seconds on and 300 seconds off. The signatures are so faint that you really just can't see it in a 300-second spectrum on. That's 5 minutes. Like in the Opus curriculum, they do 1 minute, 10-second spectra, tracking spectra of different parts along the plane of our galaxy, because in Opus, they're studying our rotation curve, and that's, of course, super close, and that's all they need. These, they're farther away, so we have to go longer, 5 minutes, but it's going to be very hard to see. So what we do is on, off, which is really on minus off divided by off. And I'll show you from the results what that does, but it helps you bring out really faint signals by getting a background with it not there that you can then use to pull out the signal that is there. So 300 seconds, then we do a 2-degree shift. I usually just shift in right ascension. The goal is to get, a handful of beams away. So I do 2 degrees in RA, none in DEC, though it really doesn't matter. The rest you can keep the same. Save and continue. I got to pick an account with some credits. Or some other account with some credits. And then you submit. I'm not going to submit because I have some of these. Now, it was a bit of a bust this year. If those of you who did the Opus Lab 7, or if you did this lab with your students, the Green Bank 20 meter, their closed loop helium cooling system has been busted. So it's been running warm. And the images turn out about the same, the pulsar timing stuff about the same. But apparently with the high resolution spectrum, that's where you see it. And so the ones that were easy became difficult. The ones that were difficult became impossible. The poor Opus students, both in Lab 7 and Lab 7 was fine. In Lab 9, they do a similar thing here with the easy galaxies. They're trying to get Hubble's law. And they only do like a minute on, minute off, which is normally enough, but it just wasn't enough with the cooling system off. So this was a good lesson for me because most of the telescopes that we're integrating do not have cooling systems. And so with the other radio telescopes, it's going to have to be much longer integrations. And we're working on how scaling works in Skynet 2. Like if you request in the optical, you request a 10-second exposure on this telescope, you may get a 12-second on this scope and a 5-second on that scope. So it knows how to scale. We're figuring out how that works in the radio and building that into Skynet 2. Anyway, it's a bit of a bust. And so the data that we'll be using, I think it's offline right now. And I think they're fixing it like right now is my guess. But we'll use some older archival data today. Okay, so you can see these galaxies down below here. Got 1, 2, 3, 4, 5, 6, 7. Got kind of 9 people in the chat, including myself. And again, here's the list showing which ones are easy and which ones are difficult. The kind of the middle 3, surfboard, hamburger, and needle, are the difficult ones. But I'll walk you through all of them. So everyone pick one and just go to the tab. But I'm hoping you all pick different ones. Go to the tab and insert your name. I'll take one of the tough ones. So I'll do surfboard. Oh, I'm sorry. I got to give you the link. Okay, there's the link. Again, Andromeda's on the first tab. Each galaxy gets its own. So pop down this list and pick a galaxy. Try to pick one that someone else doesn't get first. I took cigar. No, I didn't take cigar. But I took surfboard. And if you're sufficiently bold. I don't know why the needle, there's a number in here. I guess that didn't get deleted out. Remove that. Okay. So far, Ro and I are the only ones who are sufficiently bold. Don't be scared. You could do this. If I can't make you do it, and I know I can't make you make your students do it. So hopefully you pick one here. Okay. And once you pick one, I'm going to direct you to data.
Oh, you picked.
And that would be on this tab. This is just a document that we used at our workshop last summer. So if you go to this document and you slide down to, I think it's page, what was that? The bottom of page 4 and onto page 5, I have an example of each. And let's just take a look at them. I'll probably walk through each one just so you get a feel here. Let's start with Sculptor, which is, again, that optical galaxy that you've been downloading. And here's its on minus off divided by off spectrum. So let's first look at the on spectrum. So here's the on spectrum. And you see a blip there.
Sorry for the interruption, Dan.
Please.
Which document is this in?
This is in the second one I put in the chat.
Oh, the second one. Okay. I didn't see it earlier. Got it. Thanks.
Well, I just stuck it in right now. And the first one is where we're going to do the calculations. Okay. So I'm just looking at Sculptor right now. I'll look at each of these quickly with you, but let's just focus on Sculptor for the time being. You can see it here, but let's go to the on spectrum first. And you see a blip there. You may think, oh, that's it. But no, that's the Milky Way hydrogen. We got to look through the Milky Way. It's going to be the dominant thing. So that's the Milky Way hydrogen. So where is the Sculptor hydrogen? Being a galaxy farther away, it should be redshifted, should be over here somewhere. It's not that little blip. That little blip is RFI. It's actually kind of this plateau in here. Actually, this whole plateau. But you'd never see it. Let's look at the off spectrum, just as an example. If you go 2 degrees off, you still have Milky Way. You still have that RFI blip. And that little tiny excess is gone. But again, you wouldn't have noticed it compared to the scale of the undulations, which is instrumental response. So how do you see it? You subtract it. And then you divide by the off spectrum, which flattens it, flattens the instrumental response. And when you do that, you get what they've given you here, the on minus off divided by off. It gets rid of most of the undulations, usually not all. Tries to cancel out the Milky Way hydrogen line, but usually not completely successfully, because you are looking at 2 degrees apart. They are different bits of hydrogen that you're going through. So you'll see a sharp either excess or deficit, depending on whether the on or the off had more. And that's the Milky Way hydrogen. But what you're looking for, you can skip the bottom spectrum. Nothing will be there. It's all on the top, is to the red, some kind of broad plateau. And this is kind of the classic Tully-Fisher horn-shaped profile. If you have an edge-on spiral galaxy, you see how broad it is. Just like the Andromeda line was very broad. The center here, the center frequency, in fact, we can go to live spectrum. And you'll use this on your own. And there's a little magnifying glass, and we can zoom in here. So the center frequency is kind of the frequency that the galaxy is moving away from us. And you can eyeball, you zoom in and then kind of eyeball. And then, so you want to measure that, a central frequency, and you want to measure an edge frequency, whether this side or this side. In this case, I'd probably take this side since this side has the Milky Way hydrogen kind of contaminating it. And let's look at a few of the other options. I'll just pop through them real quick. So whichever one you happen to be working on, you can get it. This one's pretty easy. It's not horn-shaped profile. This galaxy, I think this is Bode's galaxy. I'm trying to remember the list here. No, the Cigar Galaxy. Yeah, the Cigar Galaxy's been disrupted by Bode's galaxy, and so you don't have as clean ordered flow, so you get more of a Gaussian than a horn-shaped profile. Here's Surfboard. That's the one I'm going to do. It's one of the tough ones. You can see it. It's right here. Hard to see if there's still some slant left in the channel, but I can see it in this channel where it's pretty flat. What else? Let's look at Hamburger. Here it is. See, it comes up, broad, comes down. So you'll be measuring this feature if you're doing Hamburger. And Needle. Here it is, right here. It is kind of horn-shaped, but faint. Those were the three tough ones. Then Whale should be easy. Yep, there it is right here. Kind of asymmetric. But the Whale galaxy is a bit of a train wreck, and so I'm not surprised it's asymmetric. And I think it's gravitationally interacting with the crowbar. And crowbar is really easy. You have a middle, and then the edges are kind of close. So whatever your galaxy, get rid of these, pull it up. Let's see. And I'm doing, again, surfboards. Let me reload surfboard. I'm going to go to live spectrum and make my measurements. You should make your measurements now. Mine down. I got 1417.1 for my center. Pick one edge or the other, doesn't really matter. 1416.3.
Dan, where are you?
I'm doing surfboard.
But you're making your measurements on.
Go and click on live spectrum. It's right here.
Oh, down there. Okay, I see it now.
And when you click on it, then you have to click on the little magnifying glass right down here. And then you draw a box around what you're going to measure, and it will zoom in.
I see. Perfect.
Right. So I'm going to kill those. I have my numbers. And then I'm going to come back to my board here. Great. Jonathan's taking sculptor, row. Dan and Ian both doing surfboard. Ben, David, Ross. Okay, great. Everyone signed up. Wonderful. Okay. So surfboard. What I say, my center frequency was 1417.1. My edge frequency, I'll just type it in right now, 1416.3. Then we're going to do calculations, mostly the same as last time. And I'll give you a second to enter your numbers, and then I'll walk you through the calculations. Good. Ian and I will have, yeah, you're for, yep, you got it. We'll have numbers to compare to each other. Okay, first is the line of sight velocity. Again, the equation's over here. So it's equal to the speed of light, 3e to the 5, times parenthesis, the emitted frequency. It's also listed right over here, 1420.4, minus the observed frequency, which you just measured, parenthesis divided by the observed frequency. So in my case, I got a line of sight velocity moving away from us about 700 kilometers per second. Ian got 720. That gives you an idea of kind of the uncertainty from these visual measurements. Give you all chances to catch up here.
And that's not off by much. Wow. So the
Yeah.
center frequency. So
Yeah. And you'll see while you're catching up, I'll just kind of show you my class. I have a ton of students, so I have a handful on each one. You can see kind of the variation. Usually they just disagree by about 1/10 in the frequency, the same as we did. Here's cigar, maybe 2/10 at some places. Okay, so these are getting stuck in there. Now, distance with Andromeda, we looked it up. Here, I provided it. With these nearby galaxies, it's a little tricky. It's not just use a Cepheid. There are all sorts of different techniques. This is kind of the best agreed upon distance from the experts. So I just provided it. And instead of a collision timescale, someone's ringing my phone. My wife. Hey, I'm in my Zoom with my educators. Can I call you back? She was inside on the steps coming upstairs, up to the top floor. So she was inside. So you'll find her in the house somewhere. Okay. Okay. Bye. She lost our Cocker Spaniel, but found our Cocker Spaniel on the same phone call. So, all right. Right. So last time we looked up the distance to Andromeda. We know the velocity that was coming at us. So we calculated a collision timescale. With these, they're all moving away because of the Hubble flow. So we can measure Hubble's constant. Again, recession velocity is just proportional to the distance with Hubble's constant. And this is a big part of Opus Lab 9. Here, it's just kind of a little small add-on. But you can calculate Hubble's constant. It's just the speed divided by the distance. And I provided the distance in megaparsecs. And so Ian and I are getting a Hubble's constant about 80. Hubble's constant measured just off a single galaxy is going to be a little bit rough. But we have a handful of galaxies. And there's a page here that is taking the median from each page and then the median of the medians. I guess it won't actually do the median of the medians till we get numbers in for everyone, but we'll check back on that. Extra motivation for you to actually do your calculations. Okay. What's next? So we've got the edge frequency. And again, we use, I think I just copy and paste. Yep. The Doppler equation to get the edge velocity. And then the rotation velocity is the absolute value of the edge minus the center velocity. Okay. And then you probably remember from last time, the enclosed mass is v squared r divided by g. And last time we measured the size of Andromeda from our image. In this case, what you would do if you had the time is you'd go take an optical picture, because we're not going to resolve the size in the radio. You take an optical picture, figure out its radius. But instead for this calculation, I just give the radius. Because you already got an example of how to do this with Andromeda. So that would be v squared times r divided by g, 6.67 e to the minus 20.
Oh,
And it should be minus 11, unless I'm in some weird unit. I'm in kilometers instead of meters. And then you want to put this in solar masses, so we divide by the mass of the sun, 2e to the 30. Yeah, that looked right. So I'm going to pop through here and see how you're doing. Jonathan's cranking along. was going to say, here's a completed one, but it's mine. Getting close. Needle, whale, crowbar. Yeah, I'll give you a moment here. You don't all have to complete the calculation, but I'll give you a chance there.
That doesn't look right. Oh, I'm off. That's why.
Probably need to divide by 2e⁻30.
And did you say those numbers, the line of sight was, you provided that in one of the docs, or we were supposed to look it up?
Line of sight velocity, no, that one you calculate using the Doppler effect in your central frequency.
Okay.
So you can see the equation here. The line of sight speed, it's 3e⁵. Well, the equation's right here. 3e⁵ times 1420.4 megahertz. That's the emitted line frequency minus your observed center frequency, and then divided by your observed center frequency. And same equation for edge velocity.
I got you.
Okay.
Wow, that's a huge difference on the enclosed mass, just for the
Yeah. Well,
slight frequency
same
difference.
order of magnitude. So, yeah, we're off by what? About less than 20 billion solar masses. It sounds like a lot, but compared to the 70 billion, 60, 70 billion, it's not that bad. Okay, we'll see if we have any more, and then we'll just kind of move on to the next task. So probably something off here. Oh, your rotation speed, Benjamin, is off. It should be this one minus this one, the absolute value. Here, I'll help you out here. I drag? Oh, it's not like Excel. You subtracted your edge frequencies. You want to subtract your velocities. Okay. See what else we got.
Thank you. That's probably what I'll see my students do.
Yep. That's why we got to go through these. Your students will make the same mistakes. If we can't do it, we can't expect them to do it. Yep. So typically, like the Andromeda, what did we get for Andromeda? We got a mass 2e⁻11, 200, 300 billion solar masses. So that sets an expectation. And so here you got 500 billion for needle. Surfboard, we got something a little bit smaller. Crowbar, it's close. I think you have to then divide by 2e⁻30 to put it into solar masses. That's yours, Kent. Right now you're in kilograms. There you go. Must be a little tiny galaxy. It didn't have, its spectrum wasn't very broad, so it didn't have much of a rotation speed. So that probably is tiny.
The spectrum looked kind of almost like a peak.
Yeah.
So it was actually hard to tell where the edge was.
Mm-hmm. Yep. And maybe it's not as edge on as I thought it was. Maybe it shouldn't be in the sample, because if it's face on, you don't get the spread. Anyway, I'll just take another look at Hubble's constant here. Maybe I'll take one of these out so we get means. So as a group for Hubble's constant, we came up with about 73. That's like exactly right? Okay. Anyway, so you see how that activity goes. It's a nice, they've done something similar with Andromeda. So this should be pretty easy after doing the stuff with Andromeda. Okay. And again, it's fun if you have a lot of students because, well, we all did one. Remember, each team is doing two, so you end up with more in each category. So if one team gets it wrong, it's clear compared to the other ones, and they know to go back and correct their mistakes. And so I'm a big fan of these kind of common Excel files where you just open it up to everyone in the class, and you see the numbers furiously flying in there, and it's fun. And as things are wrong, they're corrected because they see the differences with others. And here's what my students got for helpless constant. They got 67, which matches the CMB value. 73 matches the Cepheid calibrated type 1A supernovae. So somewhere in that range. All right, that's it for module 6. Any questions about module 6? It's meant to be one of the smaller, lightweight modules, kind of like the pulsar module, kind of in and out, 2 classes. All right, so module 7. So I was saying this is our galaxy's capstone. Let me pull up the guide here. Slide up a little bit. So normal and active galaxies and their evolution. And it starts with, kind of a description of galactic evolution. And maybe we'll go through some of this next time. But it tells the story. Here's the very quick summary of the galactic evolution story. The way you grow galaxies, you start with these little tiny fragments. These are from the Hubble Deep Field. And they interact with each other, merging, growing bigger and bigger things. And then you can grow from 2 further mechanisms. It could be like a spiral, and you absorb some dwarf galaxy, probably in orbit around you, and become a little bit bigger spiral. Just that little dwarf's not going to disrupt your spiral structure, so it enhances your mass, grows you. But you go through the stage that as it's merging, it disturbs the gas in a couple of ways. It disturbs the gas, and so you get a lot of gas clouds collapsing and forming stars, so you get a starburst. In the optical, you'll get more blue light. You'll get star-forming regions, so H-alpha regions will be enhanced. You'll see more dust. You'll see dust being warmed up by those stars, so that glowing in the mid-infrared. So all sorts of indicators of star formation in your optical and infrared images. But also some of that gas will sink down to the central black hole and activate it. And we talked about that back in module 4A, and we'll talk about it again in more detail next time. They get a little period of radio emission. So when you have that minor merger, you become a starburst galaxy in the optical and infrared, and then shortly after that, you also become radio bright. And then the starbursting turns off as things settle down, then the radio turns off, and you're back to a spiral just a little bit bigger. So you go through a little bit of a loop there. And then the other way you can evolve is a collision between 2 spirals. And this is a major merger. And so the spiral shapes get, spiral orbiting pattern, ordered motion gets all disrupted. And usually it gets disrupted and you end up with just disordered motion. All the gas in both of those spirals get activated. So you have an extreme starburst. And the thing gets very blue, and you get a lot of H-alpha from the star forming regions, and and dust gets blown out of the galaxy, and so it becomes very triggered in the optical and infrared, and also those black holes at the center get really fed in this case, and so you have extreme radio emission, a radio galaxy, or if you're looking edge on the jet, we call it a blazar. But when this calms down, it doesn't go back to just being a spiral because it blew through all of its gas. There's no gas left, so no more stars. And so it's an ever reddening population of stars, kind of like a globular cluster. It just gets redder and redder with time, and the motion is disordered, also like a globular cluster. So it's like a giant globular cluster. And those are your 2 basic evolutionary pathways. It can get a little bit more complicated because if you form an elliptical, it's at the center of a cluster of galaxies. I guess I don't have a picture here. Nearby galaxies can run into it and feed it. And so a central giant cannibalistic elliptical can also have some spiral properties because it keeps eating nearby spirals. But that exception aside, these are your two evolutionary pathways. And so the idea is every team in the class picks a representative galaxy from these categories. And categories are normal spirals, starbursts, which are spirals that have been activated by some kind of merger, Seyferts, so a little bit of radio emission at the core, ones that are both starbursts and Seyferts. We let them do dwarf galaxies. Also here, ellipticals and lenticulars. Lenticular is just an elliptical where it kept some of its ordered motion. Radio galaxies, which are, that previous stage. And that's it. So they're picking them from those categories. Each team picks one. And everyone wants to do a spiral or a starburst, or maybe some of the Seyferts because they look like spirals. And so from these first four categories, they pick them like crazy. They fight for them. If I haven't mentioned this before, let me mention it now. One thing I do in my class is I do a Kahoot. You know about Kahoots? Normally they're done kind of at the high school level, but the kids just love them. So the first year for target selection, whether it's they're picking galaxies or earlier on picking star forming regions or star death regions, I'd put up the list on the board and say, okay, everyone pick one and no duplicates. And they went nuts. They went in there, and if some other team took the one they wanted, they just erased that team and wrote their own team in there. And it is mayhem, but the great kind of mayhem. I realized, okay, this is something they really care about. So I always had reading assignments, and who knows if they're actually doing reading assignments. So I tried Kahoot. I was really skeptical, but one of my TAs suggested it. And the questions are just simple questions on the reading. Some of them can be fun. There's music. They're competing against each other. They get points for correctness and speed. And they can do it on their phones. And so each team has, they're huddled. They come up with an answer and quickly submit it. And whoever got the most Kahoot points get first dibs in target selection. And then once that's done, we clear the boards and they start accumulating more Kahoot points for the next target selection. And after we get done with galaxies, they still do it just because they want the most points. And I actually get swag. I print out stickers, magnets, buttons from their images they made over the semester and give them away during the final exam. And so that motivates them to keep doing the Kahoots. So they do the reading. It's surprising. They actually know the answers, and they'd only know it if they did the reading. And so it's a way to couple these things. You can get them to do the reading. It's fun. It's exciting. They get really loud and they're having fun. You want them to have fun. Anyway, and I can give you example questions. If you want to try that, contact me and I'll tell you how to get set up. Okay, so they pick a galaxy. Some of these are misclassified. I used chat from 2 years ago to figure out, is this a starburst or a Seifert? And often it's a little nebulous. Some things are on the boundaries. I need to go through and update the list a little bit. Maybe I'll do that before next week. Okay. And then they observe it in the optical. They do a big optical project. They supplement it with infrared from Spitzer or Weiss. They observe it in the radio. They do a map to see if there's a synchrotron emission blob coming from the center, the central black hole. They take an H1 on-off spectrum, like we just did today, to look for cold gas. That's also an indicator of star formation. So they're studying it in every way they now know how to study a target. So that's why it's a capstone. So we have about 15 minutes. Let's do some of the astrophotography. Was everyone able to load in their image? Okay. So we're going to go through this and you can follow along. I'll go slow. And I have some other galaxies here where I'll give some examples, but we'll try to get through this today. So this is what popped in. So the stacks have already been made. There's a V image, a green image. Sorry, that's a blue B image for blue, our image for red. We have a luminance, and it's already set up with the luminance. Should be, let's see. Blend mode is luminosity. We have the H alpha layer above it and the Spitzer layer, which, Spitzer didn't get the whole thing, but we'll use what we have. And Spitzer and the H alpha should be turned off for the time being. So we have LRGB, but nothing's processed yet. So this is our starting point after making the stacks, grouping it and coloring everything and setting blend modes. So a little bit of review first, just to get the LRGB good. And then we're going to talk about dust correction. That's the thing that's different. So the steps, just to remind you, we come over here to display settings and pick the luminance layer. It's the gray one. Okay. We link all values, pixel value, or link all layers, pixel value. Second one down. Everything's gonna get linked to the luminance layer. Okay. The idea that there is now we only have to control the luminance layer and the RGB will follow without us having to change all four of them. Then we go to photometric calibration. We've done all this before. Photometric calibration. And it should have your red, your green, your blue layers, and you click measure 0 points. It's calculating those. Okay, it's measured mine. Yours will be soon. If you clicked around the same time, you'll get yours pretty soon. And this is just the relative scalings for the red, the green, blue in magnitude space, but they correspond to factors. And the reference layer is the red layer. And so using these factors, they'll rescale everything to the red layer. Right now, let's leave extinction at 0. Kind of the whole point. The new thing that we're going to learn is about how to do dust correction in galaxies. We'll calibrate. Okay, and it should get really red because that light, that's how you would see it looking through a telescope. But the true color is bluer. There's a lot of dust in the galaxy that's reddening it. We'll fix that in a second. Something else you need to do is, well, I'll pause here, just make sure everyone's with me. Okay. You don't really have to with this one. The luminance curve is well matched to the others. We basically set the red, green, and blue layers correctly. The luminance layer needs to be in the same range. It can't be way low or way high, or else when we do brightness and contrast settings for the luminance layer, it will end up clipping colors. To maximize your color dynamic range, it needs to be synced usually to the red. So we'll go through the step, but it won't matter with this one. It's called neutralize sources. You may remember this step from before. I'm going to take the luminance layer and I'm going to neutralize it to the red layer. And it will shift and stretch. So the luminosity curve changed just a little bit, but it didn't change your image perceptibly in this case. Okay, so that's the basic. Oh, and then we set midtone. So stretch mode, it's currently in linear. It's good to go to midtone because you just get midtone, then hit default. So you won't saturate the middle. See how much more detail you have there? I'll put it back to linear just so you can see. Linear, if you want to see the faint stuff, it saturates in the middle. But if you go to midtone, you can see the faint stuff and not saturate in the middle. But nice detail. It's just the color that needs worked on. Okay. You can play games like adjusting the background and midtone level. We learned about that before. Like if I click on just the luminosity layer by itself, you kind of want to increase the background to be just below that peak. Maybe 10%, 20%. That's right at the peak. I'll do 15. Then go back here, and you'll see it will darken the background around it just a little bit. And you can make the whole thing brighter or fainter by changing the midtone level, but we'll just leave it there for now. So those are the basic steps. We've done that stuff before. Now the question is color. Now, if we're doing an elliptical doesn't have any dust, any embedded dust. So you just have to do the Milky, actually, let's start with that first. The Milky Way extinction. There's two types of dust. There's dust in our galaxy that we're looking through to see this, and there's the dust in this galaxy. So for the Milky Way dust, you go to the NED extinction calculator. Here, let me get the original link. This one, I have one typed in. Here, I'll just do it over here. NED extinction calculator. Here it is. Yeah, and I'll put this in the chat. It's all in the module too. There's the extinction calculator, and you put in the right ascension declination of your target. Normally for this, I just go to my image, I hit zoom to fit, and then I use the zoom in button to get right to the very center. And then I read the right ascension and declination off of here. Actually, I didn't do this one before, so I'm going to write that down. 004732 minus 251738. I can zoom out again. Now I'll type this in here. 004732 minus 251738. I hit go. And we'll look up the amount of dust in all the different standard bands. And what we want is B band minus V band. So not the central wavelength, but the galactic extinction. And the B band is 0.068, and the V band is 0.051. So this is 0.017, almost nothing along this line of sight. And usually that'll be the case. Most of the galaxies we observe are out of the plane of the galaxy. There's hardly any Milky Way extinction that we have to consider. We can correct for this. We won't see a change if it's that small. It has to be about 0.2 before you see a change in color. But just to remind you how, you go back to Color Composite Tools, Photometric Calibration. Under Extinction, I'll put in that 0.017. Calibrate, and it technically just got a little bit bluer, but it's not enough to see. Now, that's correcting for the Milky Way extinction. Next, we have to calculate for the extinction in that galaxy. And that's trickier because the deeper you go, there's more dust, right? It's this idea of color focus that I'm pretty sure I mentioned back when we talked about extinction corrections for star forming regions. It's like a camera. It can only focus at one distance. With this color correction, we're looking through a column of dust. We have to pick a single value. So we can only get the colors correct at a single depth in the column. Anything in the foreground will get overcorrected, and anything deeper in won't get corrected enough. Now think about a galaxy. If you go deep enough into the dust here, you can't see it anyway. If you go deep enough into the dust, it's blocking all the light. So normally I like to try two different numbers. One corresponds to the case where there's 25% more blockage in B than V. And the other case is 50% more blockage in B than V. And so those are, I'll just write them down. So case one, write this in the chat. You do the Milky Way, EB minus V, and you add to it 0.312. This is the 25% more in the B band than the V band. Case two is your Milky Way EB minus V plus 0.753. Now, you don't have to be super precise. You can just kind of play with it as well. But let's just try these two values. Now be real precise. The first one, if I add on the Milky Way, that's 0.329. And the second one, if I add on the Milky Way, it's 0.76 and 0.770. So let's see what those kinds of numbers do to this distribution here. I'll go back here. Instead of just the Milky Way extinction, I'm going to do that plus the smaller of the two, give me 0.329. This we should see. It should get bluer. Yeah, it got a little bit bluer. It still doesn't look blue enough. Normally for most spiral galaxies, you have to go with the higher number to get something that looks right. But sometimes I'll show you a case in a second where the lower number is more useful. Let's try the higher number. Set 0.329. The higher number was 0.770. Calibrate. Yeah, that's looking like the color of a spiral galaxy. Again, if we correct for more, we're correcting down to a depth where there's no light anyway, because it got blocked by the dust. Now, most astrophotography packages do this completely differently. It's kind of like a standard, you say, okay, this galaxy has the spectral distribution of a certain type of spiral, and it adjusts the colors to match that. Here in Afterglow, we coded this more physical approach because what's causing the reddening is dust. And so we can actually correct for dust. And so instead of just some kind of color palette matching, which is very artsy and abstract, this is very physical. So I like it. While you're playing with that, I'll give you another example, and we'll probably stop there for this week, and we'll continue with the H alpha layer, the mid-infrared layer, and the galaxy evolution stuff next time. But let me give you another example. This will be NGC 604. You don't have a data set for this. I'll just show it. 604, this is triangulum. So it's like it's in our local group. So after Andromeda, it's the next biggest thing. It's huge. It's like, this is just a tiny bit of the outskirts. I don't know, it's probably a degree across or something. And this is a sixth of a degree field. And I've already done all the LRGB combination, and I've turned the H alpha on in this case. We'll see more about H alpha next time. There it is without H alpha. Here it is with H alpha. And let's correct for the different levels in this case, just to show you. So photometric calibration, the Milky Way correction is 0.039 along this line of sight, which should be barely noticeable. Yeah, I didn't see anything. Now I'm going to do the lower range of that recommended. And so if I add on that lower number I put in the chat, 0.312, gives me 0.351. Yeah, so that's looking pretty good. Now, if I go with the higher one in this case, it's too much. We could talk about potential reasons why. The higher one in this case added up to 0.792. And we do this and it, waiting for it. Yeah, that feels a little too much. It feels kind of like an icy blue. The foreground stars have all been made kind of blue. So I'm going to go back to the previous one. But it's a little, you got to feel your way through it. I think with this one, since it's so close and we're looking in the outskirts, everything's spread out because it's so close. Or it could just be because we're in the outskirts and there's not as much dust here. I didn't need to do as big of a dust correction. Or it may be something between those, you know. And the student should play between those two limits and see what looks good to them. Treat it kind of as a free parameter, but they know what color stars are and blue galaxies are. Because they studied stellar colors in Module 2. Okay, I'll stop because we have 1 minute left and you all may have questions or comments. Or not. Okay. Well, if you don't,
Dan,
yeah, go ahead.
are we meeting next week with it being Memorial Day?
Oh yeah, let's not meet next week. Let's we probably would lose too many people. So yeah, we'll skip next week and we'll meet the week after. We'll finish up this galaxy exercise and we'll start working on the gravitational wave stuff, which would be fun.
Are you going to be around, Dan,
Today, or you mean next week?
next week?
Yeah. Yeah, I'll be here.
I'm just wondering if it could use it like as a catch up.
We could. Yeah, so tell you what, I'll pop in with no plan, just office hours to
Yeah.
answer questions. How's that
Okay.
sound?
Yeah, that's what I was thinking.
Yeah,
Perfect.
unless my family comes up with some plan, in which case I'll bail, but otherwise, if I'm free this time next week, I'll pop on.
Or depending on what they come up with, you've got an excuse that you don't have to.
Yeah, that's right. If they come up with something I don't want to do, then yeah, I'll be here.
Oh, sorry, gee, hate this.
Yeah.
Okay,
All right. Okay. I'll see y'all next week.
thanks, sir.
Thanks,
Thank
Dan.
you,
Well,
Dan.
in
Thank
2
you,
weeks. I'll
Dan.
see some
Yeah.
of you next week. See ya.
Thanks, Dan.
Sure,
Bye.
my pleasure. So here, let me end the record.